Hello, curious minds, and welcome back to Vibing Science. Tonight, we journey into a realm where the most common element meets one of the universe's most versatile, unlocking secrets that reshape our understanding of matter itself. We're diving deep into the microscopic symphony of organolithium chemistry, a field brimming with both profound utility and mind-bending structural mysteries. So settle in, let your thoughts wander, or simply let my voice guide you as you work, study, or drift off to sleep. Before we begin, a gentle reminder to like this video, share it with someone who loves a good scientific exploration, and leave your thoughts in the comments below. Your engagement fuels these journeys, and I'm truly grateful for every one of you. Let's explore. Welcome, fellow explorers of the unseen. Settle in. Let the hum of the universe be your guide as we embark on a journey into the heart of a silent revolution, a fundamental force that orchestrates the symphony of synthetic chemistry. Tonight, we delve into the intricate world of organolithium, the unsung architects of so many materials that shape our modern existence. Imagine, if you will, an alchemical dance where the most energetic of metals, lithium, forms an extraordinary partnership with carbon, the very backbone of life. This is not some fanciful tale, but the rigorous science of organolithium chemistry, a realm where physical properties, ingenious syntheses, and breathtaking reactions intertwine, revealing the profound power held within the carbon-lithium chemical bond. At the very core of this intricate tapestry lies the organolithium compound itself, a molecular entity where a carbon atom directly embraces a lithium atom. And within this vast family, a particular subset shines brightest: the organolithium reagents. These are the workhorses of the synthetic world, the silent agents that allow chemists to build complex molecules with precision and control. Think of butyllithium, a name that might sound unassuming, yet it is a compound that has catalyzed countless innovations, from pharmaceuticals to advanced polymers. But what makes this bond so special, so potent? Lithium, residing at the very edge of the periodic table, is a restless electron donor, eager to shed its outermost electron. Carbon, on the other hand, is a master of versatility, forming stable bonds with almost anything. When these two meet, the result is a bond that, while often depicted as covalent, possesses a significant ionic character. This unique polarity lends organolithium compounds an extraordinary reactivity, making them indispensable tools in the synthetic chemist's arsenal. They are, in essence, highly reactive nucleophiles and powerful bases, capable of initiating transformations that would be impossible by other means. Let's begin our exploration by categorizing these fascinating entities, starting with the most fundamental building blocks, the alkyl and aryl monolithium compounds. Picture, if you will, the simplest members of this family: methyl lithium and phenolithium. These are not merely individual molecules floating in solution. Oh no, the carbon-lithium unit, in its inherent nature, possesses a strong tendency to aggregate, to cluster together in intricate, beautiful arrangements. Think of them as miniature molecular communities, forming tetramers or hexamers, where several carbon-lithium bonds intertwine to achieve a more stable configuration. If you could zoom in, you would see a delicate lattice, a crystalline ballet of atoms. How are these fascinating reagents brought into existence? One of the most common and elegant methods is through a process known as metal-halogen exchange. Imagine a solution, perhaps a delicate bath, where an alkyl halide, say methyl bromide, is stirred gently with elemental lithium metal. It's a seemingly simple interaction, yet a profound chemical transformation unfolds. The lithium, ever the aggressor, displaces the halogen, forming a new carbon-lithium bond and leaving behind a lithium halide. It's a clean, efficient exchange, a testament to lithium's inherent reactivity. But the story of lithium's synthetic power doesn't end with simple alkyl and aryl compounds. There's a whole other dimension to its reactivity, one that involves the reduction of polycyclic aromatic compounds. Consider molecules like naphthalene or anthracene, those beautifully intricate ring systems, rich in pi electrons. When these compounds encounter lithium, something truly remarkable occurs. Lithium donates an electron, transforming the neutral aromatic compound into a radical anion, a species with an unpaired electron and a negative charge, stabilized by the extended pi system. The lithium, having shed its electron, now exists as a positive ion, a silent spectator in this electron transfer. This process gives birth to powerful reductants, compounds like lithium naphthalene, a vibrant green solution that holds immense potential. Lithium naphthalene, with its easily accessible electron, acts as a chemical cannon, capable of reducing a wide array of organic, organometallic, and even inorganic compounds. It's a precise and powerful tool for initiating reactions that require the addition of electrons, opening up pathways to new and complex molecular architectures. Imagine it as a gentle, yet firm hand, guiding electrons where they need to go, facilitating reactions that might otherwise be impossible. Now, let's expand our gaze and consider compounds where lithium's presence is doubled, or even quadrupled. We move into the realm of dilithium compounds. These are molecules that boast two distinct carbon-lithium bonds, and they can be broadly classified into two intriguing groups. First, and perhaps the more structurally elusive, are compounds like dilithium ethanide, CH2Li2, and its many derivatives. Here, two lithium atoms are directly bonded to the same carbon atom. These are often complex and challenging to synthesize and characterize, yet they represent a fascinating frontier in organolithium chemistry. Some of these derivatives have even yielded to the meticulous gaze of X-ray crystallography, revealing their atomic architecture in stunning detail. Picture a single carbon atom cradling two lithium atoms, a delicate balance of forces, a testament to the versatility of the carbon-lithium bond. More commonly encountered are dilithiated organic compounds, where the lithium atoms are bound to separate carbon atoms, often separated by a chain of other carbons. Take, for instance, 1,4-dilithiobutane, a compound where two lithium atoms reside at opposite ends of a four-carbon chain. These compounds are highly reactive, acting as powerful bifunctional reagents, capable of connecting two different parts of a molecule or initiating polymerization reactions. They are the molecular bridges, the structural connectors that allow chemists to build intricate networks of atoms. And then there's dilithium-acetylide, Li2C2. This compound is not merely a salt, as one might initially assume. Instead, it adopts a surprisingly sophisticated crystal structure, a distorted anti-fluoride arrangement, remarkably similar to that of rubidium peroxide. This unexpected structural complexity underscores the unique nature of the carbon-lithium interaction, a bond that defies simple classification and often reveals astonishing structural motifs. It's a reminder that even in seemingly simple compounds, the universe holds hidden depths and unexpected elegance. Finally, we arrive at the frontier of tetralithium compounds, where four lithium atoms grace a single carbon. Tetralithium-methane, in particular, has captivated the theoretical imagination of chemists. Its structure remains a subject of intense speculation and debate. Could the carbon atom in such a compound adopt a planar geometry, defying the conventional tetrahedral arrangement of carbon? This question pushes the boundaries of our understanding of chemical bonding, challenging long-held assumptions and inspiring new theoretical models. It's a testament to the enduring allure of fundamental questions, the pursuit of knowledge for its own sake, to truly understand the very fabric of matter. As we conclude this segment, take a moment to absorb the immense power and versatility of the carbon-lithium bond. From the subtle dance of aggregation in monolithium compounds to the electron-donating prowess of lithium-reduced aromatics, and the intricate architectures of dilithium and tetralithium species, we've only just scratched the surface of this remarkable field. These unseen architects, these organolithium compounds, continue to drive innovation in countless areas, shaping the materials of our world and pushing the boundaries of what is chemically possible. Their story is a testament to the elegant simplicity and profound complexity that lies at the heart of all science, a symphony of atoms orchestrated by forces we are only just beginning to fully comprehend. Rest now, and let these fascinating insights resonate within you, preparing for the next chapter in our journey through the wonders of molecular science. Having anchored our understanding in the fundamental carbon-lithium bond, we now venture into a fascinating and often counterintuitive realm, the molecular misfits. This is where the simple elegance of a single bond gives way to a complex dance of aggregation, where organolithium compounds, rather than existing as discrete, lone entities, prefer to gather, to cluster, to form intricate molecular societies. It is within these aggregates that much of their remarkable reactivity truly begins to blossom. Imagine, if you will, the carbon-lithium unit as a somewhat restless individual. It craves company, a shared existence that stabilizes its energetic nature. This inherent tendency to aggregate is what gives organolithium chemistry its distinctive structural complexity, and it's a crucial aspect to grasp if we are to truly appreciate their synthetic power. Let's begin with the most common and widely utilized of these molecular groupings, the alkyl and aryl monolithium compounds. These are the workhorses of organic synthesis, the dependable reagents that drive countless transformations in laboratories around the world. And yet, their seemingly straightforward names, methyl lithium, phenyl lithium, belie their intricate inner lives. Far from existing as simple individual molecules, these compounds, in solution and even in solid state, prefer to form clusters, often taking on highly symmetrical, almost architectural forms. Consider methyl lithium, for instance. If you were to peer into its molecular structure, you wouldn't find isolated CH3 units floating about. Instead, you'd most commonly encounter a tetramer, for methyl lithium units coalescing into a beautiful, almost cubane-like structure. Picture 4 lithium atoms forming the corners of a tetrahedron, with 4 methyl groups capping the faces. It's a testament to the powerful, yet somewhat enigmatic, forces at play within these systems. This aggregation isn't merely an academic curiosity. It profoundly influences how these reagents behave, how they approach and react with other molecules. The individual carbon-lithium bond might be highly polarized, with a significant negative charge on the carbon, but within these aggregates, that charge is delocalized and shared, leading to distinct reactivity patterns. The preparation of these fascinating compounds is often deceptively simple, echoing our earlier discussions. One of the most common methods is through what's known as metal-halogen exchange. You take an alkyl halide, say methyl bromide, and you stir it with lithium metal. What ensues is a chemical dance where the lithium, with its strong electron-donating propensity, effectively swaps places with the halogen. The result? Our aggregated methyl lithium, along with lithium bromide. It's a clean, efficient pathway to these invaluable reagents, a testament to the lithium atom's eager participation in bond formation. But the story of lithium's interactions with carbon extends beyond simple alkyl and aryl groups. Lithium has a remarkable ability to interact with larger, more complex organic structures, particularly polycyclic aromatic compounds. Imagine molecules like naphthalene or anthracene, flat, planar rings of carbon atoms, rich in delocalized electrons. When these molecules encounter lithium metal, something truly transformative occurs. The lithium, ever the electron donor, reduces the aromatic system, injecting an electron into its conjugated pi network. The result is not a simple addition, but the formation of a radical anion, a molecule that now carries a negative charge and possesses an unpaired electron, paired with a lithium cation. Take lithium naphthalene, for example. Here, the naphthalene molecule, C10H8, gains an electron to become the naphthalene radical anion, C10H8-, beautifully balanced by a Li plus cation. This isn't just a chemical curiosity, it's a powerful synthetic tool. Lithium naphthalene, with its easily transferable electron, acts as a potent reductant. It can donate that extra electron to other organic, organometallic, or inorganic compounds, driving reactions that would be impossible with less reactive reagents. It opens up new avenues for synthesis, allowing chemists to access different oxidation states and create molecules with unique properties. Now, let's broaden our view even further to compounds that feature not one, but two, or even four carbon-lithium bonds. These are the dilithio and tetralithium compounds, and they represent a fascinating frontier in organolithium chemistry, pushing the boundaries of what's structurally and synthetically possible. Dilithio compounds, as their name suggests, contain two Sealy bonds. They can be broadly classified into two distinct groups. The first, and perhaps more conceptually straightforward, are compounds where the two lithium atoms are bound to the same carbon atom. The simplest member of this family is dilithiumethanide, CH2Li2. While rare and often challenging to synthesize and characterize, derivatives of dilithiumethanide have indeed been confirmed by techniques like X-ray crystallography, offering tantalizing glimpses into these highly unusual structures. Imagine a carbon atom bonded to two hydrogen atoms and, simultaneously, to two lithium atoms. The electronic environment around that central carbon is profoundly influenced by the presence of not one, but two highly electropositive lithium partners. The more common type of dilithiated organic compounds, however, involves the two lithium atoms being bound to separate carbon atoms within the same molecule. A classic example would be one for dilithiobutane, where a four-carbon chain hosts a lithium atom at each end. These compounds are incredibly versatile and serve as powerful building blocks in organic synthesis. With two reactive Sealy centers, they can engage in sequential or simultaneous reactions, allowing for the construction of complex molecules with precision and control. They effectively act as bifunctional reagents, enabling the stitching together of molecular fragments from two distinct points. Then there's the intriguing case of dilithioacetylide, Li2C2. Now, one might instinctively think of this as an ionic salt, much like calcium carbide. But the reality is far more nuanced and reveals the covalent character that often underpins organolithium compounds. Dilithioacetylide, rather than being a simple salt, adopts a distorted anti-fluorite crystal structure, bearing a resemblance to compounds like rubidium peroxide. This structural detail speaks volumes about the significant covalent contribution to the lithium-carbon bonds, even in what might initially appear to be a highly ionic system. The carbon atoms in the acetylide unit are not merely sitting there, negatively charged, waiting for lithium cations to surround them. They're actively engaging in more complex bonding interactions with their lithium partners, leading to a unique and robust structural motif. And finally, at the very edge of this exploration, we encounter the tetralithium compounds. Among these, tetralithiomethane has captured significant theoretical attention, though its practical synthesis and definitive structural characterization remain formidable challenges. Imagine a single carbon atom attempting to bond with four lithium atoms. The conventional wisdom of valency and bonding might suggest certain geometries, but the reality for such electron-rich, highly polarized systems is far from straightforward. The very idea of such a molecule pushes the boundaries of our understanding of chemical bonding. Some early theoretical speculations even posited a planar carbon for tetralithiomethane, a radical departure from the typically tetrahedral geometry of an sp3 hybridized carbon. While this particular hypothesis has largely been superseded by more complex theoretical models, it illustrates the profound impact that lithium, with its unique electronic properties, can have on the very geometry and bonding principles of organic molecules. These theoretical explorations, even if the compounds remain elusive in the laboratory, are crucial. They force us to reevaluate our fundamental assumptions about how atoms bond and how molecules are constructed, pushing the frontiers of chemical understanding itself. So, As we emerge from the fascinating world of organolithium aggregates and clusters, we see that the carbon-lithium bond is far from a simple interaction. It's a versatile, dynamic partnership that can lead to intricate molecular architectures, profound changes in reactivity, and even challenge our most basic assumptions about chemical structure. This tendency for aggregation, for forming molecular societies, is not a hindrance, but rather a key to unlocking the immense synthetic power that organolithium chemistry brings to the scientific endeavor. And it's a power that only deepens as we move into the realm of electron transfer reactions, where lithium truly unleashes its radical touch. Welcome back, dear listeners, to another exploration into the intricate dance of the universe, a journey into the very building blocks that shape our world and ourselves. Tonight, we delve deeper into the quiet but profound power of lithium, specifically its radical touch, a force that, when harnessed, unleashes a torrent of reactivity, revolutionizing the way we construct organic molecules. Prepare to immerse yourselves in the fascinating realm where the humble carbon-lithium bond becomes a sculptor of matter, driving transformations that are both elegant and profoundly impactful. In our previous segment, we mused upon the nature of organolithium compounds, those curious species containing carbon-lithium chemical bonds, and their classification. Tonight, we shall witness their raw power, focusing on how these seemingly unassuming reagents orchestrate radical electron transfers, a fundamental process in organic synthesis. Imagine, if you will, the world of chemistry as a grand, intricate ballroom. Molecules like dancers move and interact, forming new partnerships, breaking old ones. Within this ballroom, some reactions are like a gentle waltz, a slow, deliberate exchange of partners. But then, there are reactions driven by a different rhythm, a primal force, a sudden, explosive transfer of energy, a radical electron transfer. And at the heart of many such profound transformations, you will often find lithium, the conductor of this energetic ballet. One of the most foundational and frequently employed organolithium compounds are what we call organolithium reagents. Think of them as the versatile tools in a chemist's toolkit, capable of initiating a cascade of reactions. But their true magic often lies in their capacity to act as potent reducing agents, delivering a single electron with remarkable efficiency. Consider the family of polycyclic aromatic compounds. These are molecules with multiple fused rings of carbon atoms, like miniature molecular landscapes, each with its own unique electronic topography. Naphthalene, with its distinctive scent, or anthracene, glowing under ultraviolet light, are prime examples. Left to their own devices, these molecules are relatively stable. But introduce them to lithium metal, and a remarkable transformation occurs. It's akin to dropping a small, highly charged particle into a compound. The lithium atom, with its eager single-valence electron, readily donates it to the aromatic system. This isn't just a simple sharing of electrons. It's a complete transfer. The aromatic molecule, once neutral, suddenly gains an extra electron, becoming what we call a radical anion. This newfound negative charge and unpaired electron infuse the molecule with immense reactivity, transforming it into a powerful reductant. Picture this: solid lithium metal, gleaming and silvery, dissolving in a solvent alongside a solution of naphthalene. As the two meet, a subtle but profound exchange takes place. An electron leaps from a lithium atom and embeds itself within the naphthalene molecule. The lithium atom, now positively charged, forms an ionic bond with a newly formed naphthalene radical anion. The result is lithium naphthalene, Li plus C 10H-8. Now, this lithium naphthalene is far more than just a chemical curiosity. It is a workhorse in the synthetic chemist's laboratory. Because of that unpaired electron and its negative charge, it acts as a remarkably effective electron donor, a chemical catalyst for change. It can reduce other organic molecules, helping them to gain electrons, triggering new reactions, forging new bonds, and ultimately synthesizing new compounds. Imagine designing complex organic structures, where a crucial step requires the introduction of an electron to initiate a particular reaction pathway. Lithium naphthalene becomes your key. It's used to reduce carbon-carbon double bonds, to break apart difficult bonds, and to facilitate the formation of intricate molecular architectures, not just in organic chemistry, but also in the synthesis of organometallic and even inorganic compounds. Its utility spans across the vast landscape of chemical creation. The elegance of this process lies in its simplicity and its profound consequences. Lithium, a seemingly unassuming metal, acts as the electron donor, setting in motion a chain of events that can fundamentally alter the chemical identity of other molecules. It's a testament to the fact that sometimes the most potent forces in the universe are also the most subtle. This radical touch, this ability of lithium to transfer electrons, extends beyond the reduction of polycyclic aromatics. It's a recurring theme in many organolithium reactions. For instance, the very formation of many alkyl and aryl monolithium compounds, which we briefly touched upon, often proceeds through mechanisms that involve radical intermediates, even if the net reaction appears to be a simple exchange. Consider the preparation of methyl lithium from methyl bromide and lithium metal. While the overall reaction can be written as a seemingly straightforward metal-halogen exchange, deeper mechanistic studies have revealed that this process often involves single electron transfer steps. The lithium atom donates an electron to the methyl bromide, forming a radical anion of the organic halide and a lithium cation. This radical anion then rapidly fragments, leading to the formation of a methyl radical and a bromide anion. The methyl radical then quickly combines with another lithium atom or a lithium radical to form the desired methyl lithium. It's a rapid, almost instantaneous sequence of electron transfers and bond cleavages, all orchestrated by the inherent reducing power of lithium. These radical pathways are incredibly important because they open up avenues for synthesizing compounds that might be difficult or impossible to achieve through purely ionic mechanisms. They allow chemists to access different reactivities to create novel bond formations and to design more efficient synthetic routes to complex molecules. It's like having an extra set of tools in your workshop, allowing you to tackle different types of projects with greater precision and versatility. The study of these electron transfer processes in organolithium chemistry is a vibrant and active field of research. Scientists are constantly seeking to understand the subtle nuances of these radical pathways, to control their selectivity, and to apply them to even more complex synthetic challenges. From pharmaceuticals to advanced materials, the ability to precisely manipulate electron flow at the molecular level is a cornerstone of modern chemical innovation. As we journey through the microscopic world, it becomes evident that even the smallest interactions can have the most far-reaching consequences. The seemingly simple act of an electron leaping from one atom to another, mediated by the gentle yet powerful touch of lithium, underpins an entire realm of chemical possibility. It's a reminder that beneath the calm surface of stable compounds, a vibrant and dynamic interplay of forces is constantly at work, shaping and reshaping the very fabric of our material existence. In our next segment, we will venture even further into the complex world of organolithium compounds, exploring the fascinating realm of D and tetralithium compounds, where lithium atoms begin to form more intricate alliances, challenging our understanding of molecular architecture and pushing the boundaries of theoretical chemistry. Prepare to have your perceptions of chemical bonding stretched as we contemplate structures that defy conventional wisdom and open new horizons in our quest to understand the universe at its most fundamental level. We've explored the subtle artistry of carbon and lithium dancing together, the whimsical structures of their molecular misfits, and the raw power of their radical touch. But what happens when lithium, the master orchestrator, decides to bring even more of its brethren to the party? What kind of structures emerge when 2, or even 4, lithium atoms bind to carbon? And what tantalizing theoretical questions do these extraordinary compounds pose? As we delve further into the labyrinthine world of organolithium chemistry, we encounter a fascinating class of molecules known as dilithium compounds. These are not merely organolithium compounds with 2 Sealy bonds. They are molecules that defy simple categorization, presenting us with 2 distinct families, each with its own unique quirks and challenges. Imagine, if you will, a single carbon atom at the heart of a molecule, now simultaneously bonded to 2 lithium atoms. This is the essence of the simplest, yet remarkably rare, dilithium ethanide, or CH2Li2. To a chemist, this molecule is a theoretical marvel, a structural anomaly that pushes the boundaries of conventional bonding. While its existence in its purest form is elusive, its derivatives, those variations where other atoms or groups replace the hydrogens, have been painstakingly characterized. Through the intricate dance of X-ray crystallography, scientists have managed to peer into the very heart of these compounds, revealing their hidden architectures, atom by atom. These are not just academic curiosities. They represent the extreme end of what is chemically possible, pushing our understanding of how atoms can bind and interact. But the more commonly encountered dilithiated organic compounds follow a different architectural principle. Here, the lithium atoms, instead of congregating around a single carbon, prefer to spread out, bonding to separate carbon atoms within a larger organic framework. Picture a long carbon chain, and at each end, a lithium atom firmly anchored. An excellent example of this is 1,4-dilithiobutane, where the 2 lithium atoms reside at the termini of a 4-carbon chain. These compounds are the workhorses of organic synthesis, acting as powerful building blocks, allowing chemists to stitch together complex molecules with precision and control. Their utility lies in their ability to introduce 2 reactive sites into a molecule, opening up a plethora of synthetic possibilities. And then there is dilithioacetylide, or Li2C2. Now, one might assume, given our previous discussions, that this would simply be another salt with discrete lithium cations and an acetylide anion. But the universe, as always, delights in subverting our expectations. Dilithioacetylide is not a salt in the conventional sense. Instead, it adopts a highly ordered, distorted anti-fluorite crystal structure. To fully appreciate this, you need to envision a lattice, an intricate 3-dimensional arrangement, where lithium and carbon atoms interlock in a pattern reminiscent of rubidium peroxide. This unexpected structural motif highlights the profound influence of lithium's unique bonding characteristics, reminding us that its interactions with carbon are often more covalent, more interconnected than we might initially presume. It's a testament to the fact that even seemingly simple compositions can hide surprising complexities in their fundamental architecture. But our journey into the extreme doesn't stop at 2 lithium atoms. What about 4? Imagine the audacity of such a compound, a single carbon atom somehow bonded to 4 lithium atoms. This brings us to the theoretical realm of tetralithium methane. For decades, this elusive molecule has captivated the minds of theoretical chemists. Its existence, let alone its precise structure, remains a profound mystery, a puzzle yet to be fully solved. The allure of tetralithium methane lies in the fundamental questions it poses about chemical bonding and molecular geometry. In traditional organic chemistry, carbon typically forms 4 bonds, arranging them in a tetrahedral fashion, a robust and stable configuration. But what happens when those 4 bonds are to lithium atoms, notoriously electron deficient and prone to aggregation? Some early speculations, born from the fertile ground of theoretical calculations, even posited the audacious possibility of a planar carbon atom within tetralithium methane. A planar carbon, in a saturated 4-coordinate environment, is a radical departure from the established rules of organic chemistry. It would be a testament to the extraordinary electronic flexibility that lithium can impart to a molecule. The pursuit of tetralithium, even if purely theoretical for now, drives forward our understanding of the very limits of chemical bonding. It forces us to reconsider long-held assumptions about valency and geometry, pushing the boundaries of what we believe is chemically possible. It is in these theoretical horizons, these imagined molecules, that some of the most profound insights into the nature of matter are forged. From the simple, yet aggregated, monolithium compounds that form the bedrock of countless syntheses, to the intricate dilithio species that offer diverse structural motifs, and finally, to the theoretically tantalizing tetralithium. The journey through organolithium chemistry is a testament to the surprising versatility of the carbon-lithium bond. It is a world where aggregation is the norm, where unexpected crystal structures emerge, and where the very rules of bonding are constantly being challenged and redefined. These compounds, whether real or purely theoretical, are not just entries in a chemistry textbook. They are the gears and levers of the molecular world, allowing scientists to sculpt and reshape matter at the atomic level. They are the tools that build the medicines we rely on, the materials that define our technological age, and the catalysts that drive the chemical industries that power our modern world. And in their very existence, they whisper to us of the universe's endless capacity for intricate design and unforeseen complexity, a complexity we are only just beginning to truly understand. So, as we bring this exploration of organolithium chemistry to a close, remember that beneath the surface of everyday objects, within the silent dance of atoms and electrons, lies a universe of profound wonder and intricate elegance. And sometimes, the most profound insights emerge from the smallest and seemingly simplest of bonds, like the captivating and endlessly surprising connection between carbon and lithium. As our journey through the intricate world of organolithium chemistry concludes, I hope you found as much wonder in these molecular dances as I have. From the fundamental carbon-lithium bond to the enigmatic multilithium compounds, we've only scratched the surface of how these tiny interactions shape our technological landscape and deepen our scientific understanding. Thank you for joining me on this exploration, whether you were focused, relaxed, or perhaps even dreaming. If you enjoyed this narration, please consider liking it, sharing it with others, and subscribing to Vibing Science for more deep dives into the universe's most captivating phenomena. I'm always eager to hear your thoughts, so please leave a comment telling me what resonated with you most, or what scientific mysteries you'd like us to unravel next. Until our next journey, keep exploring,